All right, last night you asked me what I was talking about with the triangles, and you had some general expressions that you were supposed to use for substitution depending on what you found in the integral. And I wanted to show you where those come from, and that if you use your triangle and draw it, you will never be unsure about what you should use. Everything is based on the right triangle, which we use all the time in trig. And remember that the three sides of the right triangle are related by the Pythagorean theorem. Also remember, if we don't know one side, like for instance, if we don't know A, we can rearrange this and find that A can be written as c squared minus b squared, the square root. So, those are some basic facts. And how are we going to use this to integrate? Well, for instance, some of the forms or radicals that we saw in our integrals had the form of c squared minus x squared. If you think about this must be the hypotenuse of the triangle. This is one side. And then this whole expression is the other side. So let's draw our triangle and label it like that. So this is c, the hypotenuse. Let's label this side as x, and then this side is c squared minus x squared. Here's my triangle I'm going to use for any integral that has this kind of radical in it. First thing I want to know is I'm always going to need to know how to write dx. So I start off by writing an expression for x. I could say that the sine of theta, is x over c. So x can be written as c sine theta, dx can be written as c cosine theta, d theta. There you go, there's our substitution for that. If we look for the radical, we notice that we can use the cosine of theta, can use the radical. And so, rearranging this, we can write the radical as c times the cosine of theta. All right? Now, we actually sometimes saw an expression that looked a little bit more complicated, where there was a coefficient in front of the x. It doesn't change too much. It just means that one of the sides is a little bit different length. This hypotenuse is still c, but now this side will be b times x instead of just x. And that's all that's really changes, and our expressions or our substitutions are just going to be minorly altered. The sine of theta is equal to b over x, bx over c. So bx is c sine theta, x is c over b sine theta, dx is equal to c over b cosine theta, d theta. It doesn't actually change anything for the radical in terms of how it's expressed. The radical can still be expressed in terms of the cosine. All right? So the other possibility is if we have an integral that has a squared plus x squared. Well, now this is the hypotenuse, And A and X are two sides of the triangle. So labeling our triangle now, we have X, we have A, and we have the square root of A squared plus X squared. Again, I want to figure out a way for my triangle to write X and dx. So I see that the tangent of theta is X over A. So X is equal to A tangent theta, and dx is A secant squared theta d theta. We can also say that the cosine of theta is equal to A over the radical A squared plus X squared. Rearranging it, we can find A squared plus X squared can be written as A over the cosine of theta, or can be written as A secant theta. All right, and then just to cover our bases, what if the form looks like this? Again, just to show you, just like in the last one, all this changes is that this side will be B times X. And so when we do the tangent of theta, we get bx over A. So x is equal to A over B, tangent of theta. Dx is going to be A over B secant squared theta d theta. Just like the last time, this doesn't change anything about our cosine expression that we're going to use to find the radical. We're still going to use the secant. All right. I think I like having these triangles and drawing them because then I can always figure stuff out and I don't have to memorize anything. And it's just a matter of thinking about how you're labeling your triangle based on the radical that you got to deal with. All right, I hope this helps.